Hello fellow problem solvers. So today we're going to be talking about the introduction to geometry, namely we're going to do a problem with similarity. Now first, what is similarity? Similarity is if you have two triangles and if you can expand and maybe rotate one or flip it along the x or y axes and then put it inside the other one such that they perfectly fit, then these two triangles are called similar. If you only need to rotate and flip it to put it in the other one, then they're called congruent. And now, if two triangles are similar, say the triangles XYZ and KLM, they're similar. Now we have a couple of conditions for similarity. So XYZ is similar to KLM. When is this the case? There are a couple of conditions to look at, but the one I'm going to focus on is the angle condition. So this is the angle rule, the AAA rule, says if the angles at X is equal to the angle at K, the angle at Y is equal to the angle at L, the angle at Z is equal to the angle at M. So if this angle is equal to this one, angle at K is equal to angle at X, this equal to this one, and this angle equal to this one, then we have similarity. And from the similarity, we gain that these angles are equal, right? What we also gain from similarity is the sides have a ratio, that these sides, this over this, this over this, this over this, is of the same ratio, the lengths of those sides. And that brings me also to the second rule, which is the side angle side rule. Because if you have two angles that are equal, you have the third one, because the third one is 180 minus the other two. And our side angle side rule says, if you have, say, the angle at X is equal to the angle at K, and then you have the ratio of the sides XY over KL. If this is equal to XZ over XZ over KM, if this ratio is the same and you have the angle, then again you can infer similarity. So these are the two major rules. There's also a third rule, which is less commonly used, and it says if you have the ratio of all the three sides, if you don't have any angles, but if these ratios are the same, then you can also infer from there similarity. Now, that's a sort of primer, sort of introduction to similarity. If you're not really comfortable with it, these are sort of the rules you look for. And what similarity gives you is it gives you all the angles are equal and all the sides, xy over kl is equal to, you can go like this, yz over lm, yz over lm is equal to xz over km. Right. This means the length of the side xy. Okay? So now with that, let's move on to our problem. We have a right triangle and a couple of things to prove. So the right triangle, this is the condition that CAB is 90. Whoopsie. Actually it says CAB. CAB is 90. And we have D here, which is the foot of the perpendicular, and we have to prove a couple of things. Now, we can make sometimes actually in geometry, you can make things easier for you. If instead of, the more you get training, the less you need to actually name these things A, B, C. But you can call the side length of this is B, C, say this is X, and this is A minus X. Or maybe let's say this is Y, and we know that X plus Y is equal to A, and this is H. These are the lengths. And now what do we need to prove? We need to prove that X times Y CD times BD is h squared. Okay, so how are we going to prove x times y is h squared? And here's where there's a thing in geometry. One thing is we can look at similarities, calculate the angles, but another way I want to also instill early on at you is that in geometry, you can look at, from what I need to prove, does that maybe give me hints for what else is true? Because when you have a problem, prove this. It means in reality, so to speak, this is true. And then you want to go back and say, okay, if this is true in reality, what is also true in reality? And maybe I can do that thing that's also in reality true and use that to prove the other thing. So here we have, if this is true, we'd have also this is h over x is y over h when we divide by xh. I write it in this way because now we have these are sides of triangles also, mind you. H, side lengths, h, x, y, these are side lengths. And we'd also have, mind you, so this is like a triangle that has h and y, that's this triangle, and a triangle that has x and h, that's this triangle. So we would have that these two triangles are similar. And now, so if the statement is true, then we have this similarity. And now, let's go ahead and try to prove the similarity. This is giving us a hint as to what to prove. It's just another way of thinking. So let's call this angle right here, let's call it Z. Okay? Now, what do we have? I invite you here to pause for 10 minutes and try to calculate all the other angles in terms of Z. Okay? And now, what do we have first and foremost in this triangle? We have this angle is 90 minus Z. Because this is 90, this is Z. The sum of the angles in a triangle is 180. So this is 90 minus Z. Now, if I look at a triangle CAB, I have CAB is 90. This is Z. And so this angle right here is also 90 minus Z. And then if I look at DAB, I have this is 90, 90 minus Z. And so this angle right here is also Z. Now, what do I have? I have angle Z and 90 minus Z. Angle Z, 90 minus Z, 90, 90. What does that mean for us? And the answer is, well, looking at the angle, angle, angle condition, we have in these two triangles, we have the angle at C is equal to the angle at A, the angle at these in triangles. Let me make clear the context in the triangle CDA and the triangle, what is this? ADB. The angle at D is equal to the angle at D, which is 90. This is equal to Z, 90. And the angle at A is equal to the angle, now this is a different angle at A, is equal to the angle at B, is equal to 90 minus Z. And from here, we can infer from angle, angle, angle rule that the triangle CDA is similar to triangle ADB. Now I'll say one thing about notation. Usually, you want to say, like, it can be confusing if you don't know the context in which you're talking about the angle A. You could be thinking about these two angles are identical, but they're in different contexts. And that can maybe trick you sometimes. So to get out of this trickery, what we do is we say the angle formed by 3 points, DAB. DAB is what forms this angle. And now we have DAB, and this angle is formed by ACD. This angle at D is formed by CDA, and this one is formed by ADB, and CAD and ABF. Like this angle is formed by CAD, and this one is by AB and D. And now you can see that this angle at A and this one are different because this one is CAD and this one is DAB. But now what do we have from the similarity? Well, from the similarity, we get that. And when you do these letters in the correct order, it's much easier for you to figure out what is it that you have. And what you have is that CD over AD is equal to AD over DB is equal to CA over AB. And now let's actually call these what they are here. We have CD is equal to X, AD is equal to H, then we have AD again, H, we have DB is Y, CA is B, and AB is C. And now from here we get what we needed to have beforehand. We get that X times Y is equal to H squared. And so that finishes up part A. Now what about this part? BA squared, which means C squared, is equal to what? BD times BC. So is equal to BD, which is Y times X plus Y. Now, how are we ever going to prove this? Mind you, here we could write C in two different ways and perhaps actually prove what we need to prove. Maybe, but that seems a bit... That's potentially a different way to go about proving this thing. But I want to also show you, I'll show you different proofs here. And so what I'm thinking of here, first and foremost, is how can I get C squared? And I can get C squared from this thing that I already have this similarity. I can get it by saying C is equal to, as I put C here, Y and H I put here, is equal to BY over H. But if I look at these two things, I'll get C is equal to BH over X. And then I'll get that C squared is in fact equal to, the H's cancel out, and we're left with B squared times Y over X. Now I need to prove then that B squared over X is equal to X plus Y. Or in other words, I need to prove that B squared is X times X plus Y. But that doesn't get me anywhere. And this is a common sort of theme when you're solving geometry. You'll try something, it won't work out, and then you need to go back and try again. Now, let's look at this in another way. We have C squared is Y times X plus Y. Let's also write this as C over X is X plus Y over C. This is what we need to prove. And now my question for you is, where do we have C over X, right? What sort of sides? And okay, C is here, X is here, okay? Where do we have C and X, Y, X plus Y? Well, this is X plus Y and this is C. So now the thinking is, well, maybe we will have a similarity because of this triangle, where we will have, this triangle, where we will have, or no, my bad. So we'll have this large triangle with C and X plus Y. And then we need a triangle with, actually this is, my bad, this is Y. I just made a mistake. We have Y, so we have this triangle with Y and C. And we have this large triangle with X plus Y and C. And so if this is true, we will have that this over this is the same as this over this. And we'll have the same angle, which means what? We'll have similarity of the triangles ADB and the triangle CAB. Now, if you're not getting this just now, it's okay. This is just a way of thinking in general. You don't have to master this right now. Now let's look at what we have from similarities. So we have this angle, Z, the angle, let me clear this up. So we have the angle DAC is equal to the angle DAC, ACB is equal to Z. The angle DBA, or actually let's go one by one. The angles ACD will need to equal, so ACD is Z. Well, actually, this is not what I've been intending to prove. This is now where I have Y, my bad. So I want DAB. So DAB is equal to ACB. And then I have ABD. ABD is the same as C. Actually, wait a second. Again, a mistake. And this is common, so you want to double check what you're doing. I have DAB, correct? D is where it's a 90. And I have ACB. Then I move by 1. I have ABD, I'm good, is equal to CBA, is equal to 90 minus Z. And then I have the angle ABD, I move by 1 again, move everything here by 1 and bring A to the other side, is BDA is equal to the angle BAC is equal to 90. And now what do I have from this? I have angle, angle, angle. From the angle, 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 we get that the triangle DAB is similar to the triangle ACB. And now what does the similarity imply? DA, which we'll now write directly as DA is H over AC is equal to what? B is equal to AB, which is equal to C over AB over CB, which is X plus Y. And finally, I have DB, which is equal to Y over AB, which is equal to C. And from here, what do I get? I get that C, when I look at these two, C squared is equal to Y times X plus Y, which is what we needed to prove, and so this is done. And now for the final bit, we need to prove that AB squared plus AC squared is BC squared. Or we need to prove that C squared plus B squared is X plus Y squared is A squared. This is the Pythagorean theorem. Now you've heard about this in all likelihood, but now we're going to actually prove this is the case. You might have taken it because somebody else told you, no, trust me, this is the case, but now we're going to actually prove this. And to prove it, we cannot use it anywhere. We cannot say that H squared plus Y squared is equal to C squared. No. We can't do anything like that. We're going to prove it by using similarities. And here, I'll invite you to actually pause for 15 minutes and try to prove this now. I hope you've paused. And here's the idea. So we have C squared is Y times X plus Y. And now let me show you some way of thinking. We have that we'll have, if the Pythagorean theorem is true, which we know it is, then we'll have C squared plus B squared is equal to X plus Y squared, right? So this is what we need to prove. We know already C in terms of X and Y. So let me write that down. I'll have, this is Y times X plus Y plus B squared is What is x plus y squared? It's x plus y times x plus y. So if I move this here, this is what I need to prove, right? This is true. This whole thing is true if and only if this whole thing is true. Now if I move this here, which means this thing is true if and only if b squared is, I'll get the x plus y out, and I'll have x plus y minus y, which is x. So if I prove this, I'll be able to prove, then I'll have this, and then I'll have the Pythagorean theorem. Now, do I have that b squared is equal to, what's it called, x times x plus y? And the answer is yes. There's two ways to go about this. One way is to say, wait a second, I can use these two similar triangles and that'll give me b squared is equal to x times x plus y. Another way is saying, wait a second, I already had this thing right here. I had initially that c squared was equal to, when I multiply these things through, I had that c squared was equal to b squared times x over y. Actually times y over x. Though actually that is faulty, I've made a mistake here it seems. No, it's b. It is equal to b over h, so that is when I take b over here, so that's when h comes here and y comes here, so it's by over h. Wait, has this been faulty? Have I made this incorrectly? X over h, so x, so x is this angle right here, then we have h at that angle, and then I have b at that angle and I have c at that angle. And when I multiply these through, I'll get that b squared, c squared is y times, okay, no, that is all good. So I have that this is equal to, in fact, b squared times y over x. Now I know c squared, what it is in terms of y and x, so I have that b squared is equal to x over y times c squared, which is equal to x over y times y, x plus y. And now these cancel out, and this is x times x plus y. So now I have b squared, and now this gives me that c squared plus b squared is going to equal, c squared is this, y times x plus y, plus b squared, which is x times x plus y, which is equal to x plus y times x plus y, which is a times a, which is a squared. And so with this, we've also proved the Pythagorean theorem. This finishes up our introduction into similarity, this first order problem where you're proving the Pythagorean theorem and learning some things about the triangle, the right triangle. And this finishes up our problems, and as always, thanks for problem solving.